Hello everyone, I'm Jaffer, and along with my team, we are here to present a project that goes beyond just textbook algorithms. We are not just comparing the codes, we are comparing the philosophies. So we start this project with a single fundamental question. How do we find the shortest path in a world that is sometimes simple and sometimes it's chaotic? So, to answer this question, we looked at two extreme ends of human society. On one side, we have saving lives. This requires speed and it requires optimism. On other side, we have stopping frauds. This requires skepticism and it requires detective's eye. So, two different problems, two different philosophies, and today we'll show you exactly which algorithm rules which world. So let's start with the first scenario, the ambulance. Imagine an ambulance is at a point A and it needs to get to the hospital at point H. So in a city, shortest distance usually doesn't matter. The shortest time is the only thing that counts. So we mapped the city as a graph. We took the nodes as the intersections, the edges as the roads, and the weights as the weights represent the time in minutes. So crucially, time can never be negative, right? We all know that. You can't arrive back to the place you left. So looking at the map on the right side of the PPT, you see the red route is physically the shorter one, but it's clogged with the traffic. So it would actually take you around 12 minutes to get to the hospital from the accident spot. So while on other hand, this green route is actually a longer one in distance, but it's clear that as there is no traffic, it would take you around 7 minutes to get to that hospital from the accident spot. So we actually need an algorithm that can aggressively hunt for that 7 minute path without doubting itself. Then here comes the Dijkstra algorithm. We call it optimistic. Why? Because its philosophy itself is greedy. It stands at a node and asks itself, what is the cheapest step I can take right now? It uses a priority queue to constantly rank the best option. It performs a process called as a relaxation where it updates its knowledge only if it finds a faster way. Because we know time is always positive and Dijkstra doesn't need to double check itself, so it makes the best option at every step, and it is mathematically proven to give us 7 minute life saving route, and that too very instantly. So now let's see the Dijkstra algorithm in action. Let's move on to the code. So let's first bridge the gap between abstract math and the reality. Instead of just naming the vertices as 0 or 1, etc., we named our indices to the first real world locations like the city hospital, main highway, downtown junction, and finally the accident spot. This actually makes our output human readable for the emergency dispatchers. Then moving on to the int main function, here we can see yeah, here we can see the adjacency matrix that doesn't just represent the distance in kilometers, it actually represents in the time in minutes. For example, take moving from hospital to the highway would take you around 10 minutes due to the heavy traffic there. But if we take a smarter route through the downtown junction, it would be much faster due to the less traffic. So the matrix is a so this matrix is actually a digital twin of our city's current traffic conditions. Then let's also have a look at about the Dijkstra algorithm in this function. So inside the algorithm, we use a loop to perform a greedy selection. We constantly ask ourselves like which unvisited location is currently closest in time. Then once we pick that node, we perform the relaxation. We check if going through this new node offers a faster path to any other neighbor. If it does, we update the time array and store the path as parent array. Here we do the updations, the time array and the path array. Well, now let's run this code. Yeah, here is the result. Dijkstra analyzed the graph and it rejected the direct highway route because of the heavy traffic there. Instead, it found a optimal route from the city hospital to the downtown junction and then to the accident spot. It also gave us the estimated time, the 7 minutes. Okay, so in emergency services, this efficiency itself is the thing that saves our lives. Well, by till now, we have seen how to save lives, but stopping a crime requires completely different mindset. So I'd like to hand over this to Rishi to take us into the dark side of the graph theory, the financial frauds.
Hello everyone, I am Rishi. In this project, where we are presenting the single source shortest path algorithms, not merely to solve a graph, I am here to show you how Bellman-Ford algorithm can act as a security tool. I will demonstrate the Bellman-Ford algorithm not just to solve a graph, but to build financial fraud detection engine. To understand how this works, we first have to answer a fundamental question. How do we turn money into a graph? In our system, we model the financial market like this. The nodes are the bank accounts or currencies like US dollars, euros, or Japanese yen. The edges are the transactions that move money between them. The weight is the most critical part. In a standard map, weight is distance, and you want it to be positive. But in finance, we have profit. If I pay a fee, that is a positive cost. But if I make a profit, that is a negative cost. Therefore, in our model, a weight of minus 5 is not a distance, it represents a financial gain of 5. This brings us to the crime. Look at this loop here. We start with $100, we converted that to euros, and then we converted that to Japanese yen, and this one we again converted it back to US dollars. And the anomaly that we see here is the $100 which we have started has grown to $105. Due to a hidden loophole in the exchange rates, we end up with $105. We created money out of thin air. In graph theory, this is called a negative weight cycle. A standard algorithm like Dijkstra is blind to this. It assumes all costs are positive and will give you a wrong answer or crash. But a financial criminal sees this as an infinite money loop. We needed an algorithm that could hunt this down. And this is why we implemented the Bellman-Ford algorithm. We are not using it to find the shortest path. We are using it as a forensic scanner. Here is how our implementation works. Unlike greedy algorithms that rush, Bellman-Ford algorithm patiently relaxes every single transaction in the market V minus 1 times, where V is the number of edges or the currencies which we have previously spoke about. It propagates the value across the entire network to see true costs. After the complete math is done, it performs one final pass. It asks a simple question. Can I still generate more profit by going around this loop again? If the answer is yes, it knows a logical impossibility exists. It immediately flags a negative cycle, identifying it not as a path but as a fraud ring. Now let's see this implementation in the form of a code which will implement in better understanding. So firstly, we'll start with this structure, the struct edge. This little block defines a transaction. It says that every transaction has a source account, has a destination account, and a weight. And this graph, the struct graph, is the our market. It holds all the currencies. The V is the currencies and E are the transactions, which are represented using edges. And now we will see the main function, how we set up this. We have initiated four currencies and then five transactions, and then we link them together. Account 0 sends to account 1, account 1 sends to account 2, account 2 sends to account 3, and so on. Like this, transactions are implemented. And look at this transaction 3 here, the Japanese yen to euro. Here we gave it a weight of minus 5. This is the minus 5, the negative cost that I explained earlier. It tells the system that this is the specific trade that generates a massive profit. This is the loophole that we want to catch. Now let us move to the engine function, which is the Bellman-Ford function. This is the function where the Bellman-Ford algorithm's logic takes place. And first we set up the value of all the distances to infinity, and then we set the source distance to 0. This is like cleaning the board before we start investigating. And now this loop will check all the edges. I mean, it will relax all the edges v minus 1 times as we discussed earlier. And it will check all the edges in the graph. And if the distance is not infinity and the distance of u plus weight is less than distance of v, which is the core logic of the Bellman-Ford algorithm and also the Dijkstra algorithm, the distance of v is updated as distance of u plus just and plus weight. The weight is this one. The weight is this here. So if this is less, it will be implemented here. So after this loop, it should actually stop working. Like if we run the loop again, it should not show any updation. That is when Bellman-Ford is correctly working, or that is when we can say that there is no negative cycle. But this loop, this part here is for checking the negative transaction. Like if this part will check for the negative weight cycles. So this is the most important layer. This is the fraud detection layer. So now we'll again run this. We'll again see this. If this is true, like if we are again getting a shortest edge, like if we are getting a shortest path again, this shows that there is a negative cycle in the graph. This will print an alert here, like the fraud pattern is detected and negative weight cycle found in the graph. Loophole allows infinite profit generation. The affected accounts are these two accounts. Where the condition is true, that is the accounts that are affected. So like this, we are implementing the Bellman-Ford algorithm. If it does not go through this if conditions here, it will print like system is secure, no fraud rings detected. But the graph that we have given here is the graph that we have discussed in the PPT, which has the negative weight cycle. That is why the $100 has become $105 at the last. So this program, when executed, should show like a fraud pattern is detected, and the a loophole allows infinite profit generation. Now we will check this out by running the code here. So yeah, if we you can see here we ran the code, like it is analyzing the transaction network, and the which is like here. It has already completed. The Bellman-Ford algorithm has been completed. Like V minus one, it has relaxed. But after V minus one times, it has relaxed. No, it should not. I mean, even if we start iterating again, it should not change. But it has changed in this condition, which shows that negative weight cycle is found in the graph. And this is the loophole that allows in infinite profit generation. And these are the affected accounts. So like this, we use the Bellman-Ford algorithm to detect the fraud transactions. So yeah, to simply summarize, a simple project would just output a number, but our project demonstrates that Bellman-Ford is a security control tool. We use Dijkstra when we need to pay a speed to save lives. We use Bellman-Ford when we need truth to stop fraud. By correctly modeling money as a graph with negative costs, we turned a standard algorithm into a shield for the banking system. Thank you.
So, hello everyone, my name is Manikanta and this is my roll number. Now, so far we have learned about how the Dijkstra's and Bellman-Ford algorithms works. Now, let's look at the hard data. We ran head-to-head battle. Uh, we didn't just uh, we didn't just run one simple test. We have built a custom C engine to automatically generate the 6 different battlegrounds. Like uh, we have uh, like we tested on positive weights, negative edges graphs, and negative cycle graphs, and we have tested some structures like sparse graphs and dense graphs and some uniform graphs also. And we have measured metrics in time, and we measured two metrics like execution time in microseconds and correctness. Now, before we see the results, I just want to quickly show you the engine we built to make this for. So yeah, this is the code we have written. Now look at our graph structure here. We have designed hybrid structure. We have designed an adjacency matrix for Dijkstra algorithm and an adjacency list for Bellman-Ford algorithm. Now, this create graph and Dijkstra's algorithm and Bellman-Ford algorithm are already known, so I am not explaining here. Now let's get into our main heart of this program, the generate scenario function. Instead of hard coding a graph, we wrote a logic to build them dynamically. Like we have included all the cases in one function only so that we can test each case separately. Like in for scenario one, we have positive weighted graphs, and for this scenario we have graph with negative edges, and for next scenario we have negative weight cycles, and for next scenario, we have sparse graphs and then dense graph, and finally for uniform weighted graphs. This ensures our test is random and unbiased. And now let's look at how we calculate the time using in this program. We are using this clock function to calculate how the CPU executes the time before and after running the program, and we are calculating by doing the uh, end of the program minus start of the program by clock per second. This gives the exact time so that we can compare easily. Uh, now let's see what this code actually outputted. Uh, Yeah. Now see, for round one, we have conducted a speed test. Uh, uh, we ran the code on standard positive weighted graph. See, the difference is clear. The difference is huge. Look at the chart. Dijkstra's, which is the green bar, finished in 50 microseconds, whereas Bellman-Ford, it has taken 850 microseconds. This is an exponential difference. Why? Because Dijkstra smartly prioritizes the best path and ignores the rest, whereas Bellman-Ford blindly checks every single edge over and over again. If you need speed, Bellman-Ford is not even in the race also. Uh, but whereas for small quantity, Bellman-Ford is best where rather than Dijkstra, because sometimes for smaller values, brute force method will be better. Um, and now for round two, we have the scalability test. Uh, uh, we used our generator to increase the number of edges to see how they handle pressure. Now look at the curve. The green line is Dijkstra. It stays low and flat. As uh, it scales efficiently. The green line is the blue line is Bellman-Ford. As the graph gets denser, its execution time shoots up vertically. On a dense network, Bellman-Ford becomes practically unusable. By this, we have uh, explained the analysis of Bellman-Ford versus Dijkstra. Now, next topic will be explained by Dhanush Kumar. Thank you.
Hi, hello everyone. My name is Dhanush Kumar Reddy, and now I'm going to explain the choice test. Before we continue, let me start with a reminder speed is great. We all love speed, but speed means nothing if the answer is wrong. Algorithms are like people. Some run fast but understand only perfect conditions. Others are slower, but they survive storms. And today we put our algorithms directly into the store. The Chow's test. Now, this is the moment we have been building toward. This is round 3, the Chow's test. Until now, our graphs have been safe, positive weights, no surprises. But in the real world, problems don't behave that nicely. So we introduced Chow's, negative weights, and the ultimate nightmare, negative cycles. What happens when Chow's enters the graph? First, we fed with this Chow's tick graph into Dijitra's algorithm. Now remember, Digitras is brilliant when things go well. It's fast, efficient, elegant. But the moment we introduced a negative cycle, everything collapsed. The output was shocking. Error. Digitras didn't just fail, it could not comprehend what was happening. It kept looping, kept calculating, kept trying to make sense of a world where distance decreases. Because the Digitras lives in a positive world, it's optimistic. It assumes costly only go up. So when start going down, it loses its grip entirely. Now enter Bellman-Fold. Now let's shift our attention. Let's run the exact same chaotic graph through Bellman-Fold. And look at the result. Success. Negative cycle detected. No crash, no infinite loop, no confusion. Bellman-Ford saw the trap, recognized the cycle, and reported it It handled chores with human maturity. In a stable environment, Bellman-Ford and Dijkstra seem equal, but the moment unpredictably enters the system, Bellman-Ford becomes the only survivor. Now we are going to the judge's scorecard. Let's break down the scorecard. Speed. Digitra's wins hand down. It is the fastest algorithm for the shortest paths in the graphs without negative weights. It's like a sports car, smooth, fast, and efficient. And next one is implementation of weights. Again, Digitra's. It has a clear structure, fewer steps, and is more initiative to implement. Bellman-Ford, on the other hand, requires multiple relaxation rounds, more lines of code. Handling negative weights. Now things start changing. And Bellman-Ford means this round. It was built specially to deal with such situations and deleting negative cycles. This one is not even a competition. Detecting negative cycle is something Digitras cannot do at all. Bellman-Ford, it is the only detects them. It clearly points them out. Overall versatility. Finally, when which algorithm can survive in the widest range of environment? Simply slightly, the winner is Bellman-Ford. It's slower, yes, but it is reliable, robust, and it works even when the terrain gets unpredictable. If we compare them in human terms, Digitras is sprinter, brilliant on a perfect track, unbeatable in speed. Bellman-Ford is a tank, slower, heavier, but unstoppable regardless of obstacles. If your graph is clean, predictable, and positive, choose the sprinter. If your graph is messy, chaotic, and uncertain, choose the tank. So when we ran the choice test, only one algorithm made it through. Digitra is elegant. Digitra is fast. But Digitra's collapse in chores. Bellman-Ford. Bellman-Ford survives everything. And that's, ladies and gentlemen, and that's it. And now I'm going to explain the code for this, what I have discussed. And the program is the performance comparison between Dijitra's algorithm and Bellman-Ford algorithm under different graph scenarios. In the scenario 5, in the output, this is the code, and in the scenario 5, you can see that the vertices are 100 and the edges are 15. The graph contains negative weight edges but no negative cycles. What happens here exactly? Digitras assumes all weights are non-negative. In this program, whenever a negative edge appears, the adjacency matrix marks it as an INF, essentially making Digitras ignore negative edges. Bellman-Ford can properly relax negative edges. So we can see the interpretation. Digitras is faster because it has a time complexity of order of n square for matrix version. Bellman-Ford is slower because it runs in the order of vertices into edges. Order of vertices into edges. So final winner is in the times of faster Digitras. Digitras fails in the scenario 6. In the scenario 6, it fails because the vertices are 10 and edges are 15. A clear negative cycle was manually created. What happens here? Digitras fails because it cannot process the negative cycles. It simply runs but gives meaningless results. Bellman-Ford detects the negative cycle by checking if any edge can still be relaxed after V1 interactions. Results. Digitra's time is 0.0002 seconds. Bellman-Ford time is 0.0002 seconds. Winner is Bellman-Ford. Even though Digitra is faster, it cannot detect the negative cycle. Bellman-Ford correctly prints that a negative cycle exists, proving it is the reliable algorithm in chaotic moment. So, overall meaning Digitra is extremely fast but only works on positive weight graphs. Bellman-Ford is slower but is extremely survivable in negative edges, negative cycles.
Hello everyone, I am Satyamurthy. I am going to discuss about the difference between Dijkstra and Bellman-Ford algorithms. To the point, we have compared numbers, execution times, and theoretical behavior. But algorithms don't live in textbook; they live in real world. On the slide, we see how each algorithm becomes a hero in different environments. To the left, Dijkstra algorithm rules the domains where everything is stable and predictable. In network routing, routers calculate the fastest path of per data packets, no surprises, no negative weights. In social media, platform find the best connections between users. In gaming and telecom, Dijkstra optimizes movement and communication pathways. Here, the world is positive, so Dijkstra shines. But reality isn't always positive. On the right, we enter a world where costs fluctuate, where values can drop, where cycles can form, and this is where Bellman-Ford becomes essential. In logistics, shipping rates change constantly, something behaving like negative weights. In currency trading, even a tiny inconsistent can be a a real world negative cycle. In chemistry, reaction absorb or release energy, just like weighted graph with gains and losses. So the real story is this: Dijkstra is the master efficiency in stable environment. Bellman-Ford is the guardian of correctness in predictable ones. Each algorithm excels not in theory, but in the type of reality it is built for. And this brings us to the most important message of the entire presentation. We often ask which algorithm is best, but it's the wrong question. Because in engineering, just like in the life, there is no universal best, only what fits the situation. If your world behaves like traffic consistent, structured, always moving forward, then Digista is your perfect partner, fast, reliable, efficient. But if your world behaves like financial markets or chemical reactions, where values grow up and down, where unexpected loops appear, then Belmont Fold isn't just useful. It's the only algorithm that keeps you safe from disaster. The goal was never to solve a graph, it was to solve the systems that run our world: traffic network, fraud detection, communication systems, logistics, and more. So, the real engineering wisdom is this: don't choose the algorithm that performs the fastest, choose the algorithm that understands your reality, because in the end, the path you take matters only if it leads you to the correct destination. Thank you.